Hey, I wanted to talk to you today about what's called the kinetic theory of gas. Um, Gas is kind of important because A, we breathe it and have to have it to live, but also because it's in a lot of things that we do. Your car engine, for example, has gas in it, gasoline, but also it's in a vapor form. It's in a gas state. And when we compress that gas, then we can get some work out of it as it burns, it expands. All of that understanding comes about because of physics, and it changes our world. We have a car that takes us somewhere instead of having to hitch up the horse and or walk or something. So it's kind of important stuff here. And this little picture I thought was kind of interesting. You got some kids in a bubble house. First of all, it's gas that's holding this whole thing up, right? So there's a blower somewhere, and they've inflated this thing. And then the kids get in there and bounce around, and sometimes they bounce off the wall, and sometimes they bounce off each other, like the gas molecules do, right? Those gas molecules are constantly moving, constantly bouncing off the walls of this thing and off of each other in the same way that the kids are. So let's talk a couple here things about the kinetic theory of gases. There's some assumptions here I want to make at the beginning of this. When we say gas, we mean particles that are small and they have lots of empty space between them. So when we say small, they are very small, but they're also, there's a lot of empty space around them so that they are, compared to the space that's available, they are taking up a small part of that. They're in constant random motion, and they interact only in elastic collisions. Remember, elastic collisions had no loss of kinetic energy. So these things are continually bouncing off each other in the walls and everything, your forehead, whatever. But they're not losing energy as they do that. If they did, then they would slow down and they would eventually all fall to the floor. And we don't see that happening. So that's why we say these are elastic collisions. That's where pressure comes from. When you blow up your tire, all those molecules are trapped inside your tire, and they bounce around and they hit the wall of the tire, the inside wall of the tire, and they push it out. A balloon would be the same way. If I changed the volume, then that would mean that it was hitting the wall less often, and so I'd have less pressure. If I took a balloon and compressed it, if I shrank it down into a smaller volume, then the molecules would be bouncing off the walls more often because there's less room to bounce around in there, and that would make more pressure. So just kind of think about this from the molecules' point of view, and maybe even the kids in the bouncy house. We talk about something called the ideal gas law. Now, this is the way that chemists typically approach the ideal gas law, like you see here. PV equals nRT. They have some different units or different constants depending on which set of units you want to work with and stuff, but I'm going to do it this way. The P is for pressure, V is for volume, and T is for temperature. And that's the important part of all this. Volume, pressure, and temperature are related by the ideal gas law. All right, so if you want to know how the pressure and the volume and the temperature hook up, this is what you're looking for. N is a constant. It says how many moles do you have in there. Now, mole is a certain number of things. If you go to the donut shop and you get a dozen donuts, that's 12 donuts, right? A dozen means 12. Right here, a mole means 6.022 times 10 to the 23 somethings, thingies, right? And you could have a mole of school buses, or that'd be a whole lot of school buses, probably cover the planet, but whatever. Anytime you get that many things together, you've got a mole of them, like a dozen donuts would be a dozen. R is a constant right here, 8.314 joules per mole Kelvin. That does two things. It scales this whole expression and it fixes the units here. Again, if you're in chemistry class and you're using different units, then you are going to have a different constant right there, and that's okay. The math works out the same and everything's adjusted for. All right, but please understand that the pressure and the temperature must be absolute. When I say absolute right there, I got to have absolute pressure. Remember, we could find the pressure at a depth in a pool or underwater or something. From first semester physics, you should have seen that the pressure under a certain amount of water was equal to the density of the water times g times the depth at which you swim. All right, and all that water is pushing down on you. But that's called the gauge pressure. We don't want the gauge pressure. We want the absolute pressure, and we had to add atmospheric pressure to that to get there. Secondly, the temperature has got to be an absolute scale. So that's Kelvin. You're kind of reminded of that right here. See how in this constant, there's a Kelvin right there on the bottom. So if I've got a Kelvin on the bottom right here in R, then I need a Kelvin right here in temperature to cancel that Kelvin and make the units work out right. If you put in Celsius, if you put in Fahrenheit, if you put in anything else, it's not going to work out right for you. All right? So that's the ideal gas law, the way chemists typically use it. And if you go to chemistry class, you spend a lot of time doing this. Here's a little example real quick. It says determine the volume occupied, volume of gas, it's supposed to say occupied by 2.34 grams of carbon dioxide at 20 degrees Celsius. So that's room temperature right there. And again, this is kind of not what we're interested in doing with it, but this little part right here is kind of the chemistry part of this. It says that if you have 1 mole of carbon dioxide, that's 44 grams. We don't have 44 grams of it. We've only got 2.34 grams, so we have a part of a mole, a fraction of a mole. We need to know what that number is. If I take the 2.34 grams and I divide that by 44 grams per mole, then the number that comes out here would be 0.0532. That's kind of rounded off. The gram on top is going to cancel the gram on the bottom, and this mole is going to invert and multiply, come up top like that. That is N. N was the number of moles. How many moles do we have? We have 0.0532 moles. All right, so that's the first thing that you've got to do there. Next up, you got to come through here and write down the ideal gas law. PV equals nRT. All right, it's just a formula. We know how to work with formulas. They want us to find the volume. That's right there. Pressure's in my way, so I divide both sides by the pressure. It would look like that. Okay, and we can put the numbers in here. The number of moles in, we've already found that to be 0.0532. R, that's that number again, so I'm going to bounce back here, 8.314 joule per mole Kelvin. And then the temperature, tempting to come along here and put in 20 degrees Celsius, but you see how the degrees Celsius and the Kelvin don't get along. This is not a difference in temperature. This is a single temperature. So this isn't going to work right here. What we need to do is not put this, but put the temperature in Kelvin. I need to add 273 to that. Would give me 293 Kelvin. It makes a pretty big difference there. All right. The pressure. This is this is in the room, so this is atmospheric pressure. Didn't explicitly say that. Sometimes it doesn't. But that number would be 101,300 Pascal. In chemistry class, you might well put 1 atmosphere right there, but then this is going to be a different number that's built in atmospheres instead of Pascal. So here again, we kind of like the Pascals for pressure. I'm going to punch this up real quick, but I think you can see that this isn't hard to do. I got 0.0532 times 8.314 times 293, and that's all divided by 101,300. And if I got everything in the right place, then you get this little bitty number here, 0.00128, let's call it. Okay, and that's supposed to be the volume of this thing. And we say, well, I wonder what the units are. So let's take a second look at the units. And of course, this thing's going to give me fits here, but this mole cancels that mole. This Kelvin cancels that Kelvin. I got a joule on top and a Pascal on the bottom. So what does that turn into? A joule per Pascal. Remember that a joule is a Newton meter, and a Pascal is a Newton per meter squared. When I invert and multiply, I'm going to have Newton meter times meter squared over Newton. Newtons cancel, and I'll get cubic meters right there. So that's the unit that we end up with on this thing, like that. That is a small number, but remember that a whole cubic meter would be a box, 1 meter by 1 meter by 1 meter. That's a big box, and we're only talking about 2 grams of carbon dioxide, so it's going to take up a little bitty part of a full cubic meter right there. That's an ideal gas law problem. Lots of other ones, sometimes they add gas or subtract gas, and you got to add or subtract stuff, and you know, that's not the trickiest ideal gas law problem we could do right there, but I think you can see how that works. Couple tip-offs here. They're talking about grams of carbon, they're talking about moles, stuff like that. So let me show you a little thing here. If I take the ideal gas law as the chemists use it, I can turn it real quickly into this right here. And let me show you the steps involved with that. First of all, I'm going to divide both sides by T. That gives me PV over T equals NR. All right. Remember that N was a constant. That's the number of moles that's trapped inside the balloon, the tire, whatever this thing is. R is a constant. And when I multiply a constant times a constant, I get a constant. This is always the same number. You trap some gas, and the pressure times the volume divided by the temperature is always the same number for the gas in that tire, in that balloon, in that piston in your car, whatever you have there. If you change the pressure, it's going to change the volume or the temperature or both. If you change the volume, if you shrink it down, that will raise the pressure, might even raise the temperature. Okay? So different things can happen. Those 3 variables are tied together by the ideal gas law. But I could take we'll take a little red balloon here because I got red up. Okay? There's a balloon, and there's gas floating around in this thing. And I'm going to take a hair dryer and point it at this thing and heat it up. That's going to change the temperature. If I change the temperature, it changes the other things, and when I heat it up, it's going to expand. So now I have a bigger balloon. This would be time 1 and this would be time 2. But what I know is that the pressure times the volume divided by the time here is equal to the pressure times the volume times the time over here. And so this is kind of what we're more interested in here. The chemists get all excited talking about how many moles they have and what the constant is, and all, you know, all the units and all that conversion stuff they just love to do. We're really interested in saying, how big is my tire going to get? How much pressure is going to be in this thing? So we're kind of more interested in that part right there. Again, let me remind you that we're tying volume, pressure, and temperature together, but that the pressure and the temperature must be absolute. So here's a little problem that might look more like what we're trying to do with this. It says if I have 2.3 liters of gas at 15 degrees Celsius and it's at 15,000 Pascal, that's not a really high pressure, by the way. That's pretty low. But that's kind of the first set of information. See how I've got a volume and a temperature and a pressure? And then I'm going to heat it. There's a new temperature It's in the same rigid container, so that my volume's not changing. They want the new pressure. What you need to do here is say this is my volume 1 equals 2.3 liters. Can we live with liters? I don't know. Let's see what happens. Temperature 1, 15 degrees Celsius. Pressure 1, 15,000 degrees, not degrees, Pascal. All right. And then when we heat it up, the volume stays the same because the volume is rigid, and it doesn't expand or contract or anything. Temperature 2, it went up to 36 degrees Celsius, and they're asking for the pressure. All right. So you see the difference in the first problem back here. Nothing changed. We had some gas, and they wanted to know one of the variables when we knew all the other ones. In this type of problem, though, here's some gas. It got heated, it got cooled, it got compressed, it got expanded. Something changed in there. So we're going to switch over and use the other version of this thing, and that will take us where we want to go. I'm going to write down P1V1 over T1 equals P2V2 over T2. That's all we got to do. Volume 1, volume 2 is the same number, so I can actually cancel that out. It's on the left, it's on the right. V1 equals V2, so those can go away. I'm left with this much right here. They want the new pressure. They're looking for P2, so I got to get rid of T2 there on the right hand side. I'm going to multiply both sides by T2, and there's P2 right there all by itself. Okay, now I'm going to do this wrong real quick. See if you can tell me what I'm doing wrong here. Pressure 1 is 15,000 Pascal, and temperature 1 is 15 degrees, and temperature, I'm sorry, I got the wrong one in there. That's 36. Let's see here. 36 degrees Celsius. I need T2 on top, and T1 would be 15 degrees Celsius right there. And when I punch this thing up, I'll get the new pressure almost. That number is 36,000. And because my degrees Celsius cancel, my units would be Pascal. I was looking for a pressure, so I feel pretty good about that, and I leave it on my test question, on the test paper. And when my test paper comes back, it looks like this because I used the wrong units. See how I got degrees Celsius there? That's not right. That's got to be in Kelvin. It didn't explicitly say this was absolute pressure, but it's kind of understood that it is. Physics books aren't really explicit on, so generally if you can kind of work it and check the answer and see if you got the right one, and if not, then go and add atmospheric pressure to this. So that's the wrong answer there, but I wanted to just do that just to draw attention to the fact that this really does make a difference here. Let me start at this point again. P1 T2 over T1 is P2. What I need to do is to come in here and add 273 degrees to both of these and get the T1 and T2 in Kelvin. Those numbers right there would be 288 and 309. Okay, that's what I should put in. So pressure 1, we got that one right, 15,000 Pascal. T2 is 309 Kelvin, and down here I've got a 288 Kelvin. This is the easiest thing to mess up right here, and just try to remember that. You don't even have the unit there to kind of guide you. We canceled that out, but I really should get something like 16,100 Pascal. Okay, a very different answer Then we got over here 36,000. It's not even close. Okay, so just be very careful with that. Remember to always use Kelvin. And if it doesn't say that it's an absolute pressure, if it doesn't say it's a gauge, if it does say it's a gauge pressure, you need to change it to absolute. But if it doesn't say, I'd probably just run with it the way it is, and check the answer if you can. Okay. I'm not going to try to be tricky like that. If it's gauge pressure, I'll tell you it's a gauge pressure. How about that? Okay. I got two special cases of the ideal gas law here that I wanted to talk to you about. This one's called Boyles Law, and Boyles Law comes about when the temperature is constant. Okay? Now, if I write down what we just wrote down about the ideal gas law, you can see real quick that if T1 is equal to T2, then these are going to cancel, and I'll be left with that, and that's Boyles Law. All right, now we're kind of going backwards in history here. Boyles Law came along before the ideal gas law, and there's this other one I'm about to show you. There were all these connections between pressure and volume and temperature, and pressure and temperature, and all these connections, and they merged those together to get the ideal gas law. But this one came along first. It's called Boyles Law. I wanted to show you the little animation thing over here with this. So let me get this going. You can kind of get dizzy watching this, but the idea is that my temperature is staying constant. So right there you see the gauge for the temperature. I'm adding enough heat to keep this at the same temperature, and then as I pile more weight on here, that weight is pressing down, which is contracting the gas. As it contracts, as the volume goes down, the pressure goes up, and I get a little curve that goes back and forth like that. All right, if I take weight off, then the gas is going to push that piston back up, and the volume will expand, but the pressure is going to drop at the same temperature there. So everything there, the temperature stays constant. I can cross it off, and I've got that simpler version right there, like that. I don't know that that's worth writing down as a special case, because it's so easy to just cross off the T's if they're the same number. All right, so you may hear about Boyles Law. It's just this right here, and does that. Now I also have something called Charles Law, which is also known as Gay-Lussac's Law. Charles was a British guy. Gay-Lussac was a French guy. They're still fighting about this 200 years later. Okay, but the assumption we want to make here is that the pressure is constant. So this time around, my pressure is stuck at 1.5 atmospheres, and my temperature, see how I'm heating it? As I heat it, it expands. As it cools, it contracts. All right, and there's my line right there. As I heat, it expands. As it cools, it contracts, and it goes back and forth on that line right there. Now in thermodynamics, we've got a lot of these processes where pressure is changing, and that changes the volume, or we change the temperature and that changes. These little graphs are kind of important and kind of nice to be able to think about that gas in there. Here's a piston, and I've got some trapped gas in there, so the ideal gas law is applicable. As I change one thing, it changes the other ones. We could come in here and remember that I used to have P1 and P2 right here, but it's the same number. It's 1.5. So I just cross those off, end up with Charles Law or Gay-Lussac's Law, and that's a second special case. Again, I don't think that's worth writing down. The ideal gas law does that, and you just cross off the P's. So that's kind of your backwards tour through history there. Let me tell you a little bit about how much energy these have. If these molecules have mass, which they do, and if they have velocity, which they do, then mass and velocity means that I've got kinetic energy. And I'd like to be able to find that kinetic energy. Now you remember that we know how to calculate kinetic energy. That's simply 1/2 the mass of the molecule times the velocity of the molecule squared. Okay? Well, that's nice, but we're not talking about this in terms of velocity. We're talking about it in terms of temperature. And from the beginning of this, we said that as you add heat and raise the temperature, the molecule moves more. It's going to vibrate more. It's going to spin more. It's going to move more. So this is a nice little expression here to get the average kinetic energy. There's a whole lot of molecules of oxygen in the room that I'm sitting in. Some of them are moving really fast. Some of them are moving really slow. And then a fast one knocks into it and makes the slow one go fast, and it slows down. It's like a big game of pool. My kids we used to go to Thanksgiving at my aunt's house, and she had a pool table down in the basement. And all the kids, we had 6 kids, they'd all run down there, and they'd hang their arms over the sides and knock the balls back and forth. And there were just constant collisions going off everywhere. The room is like that with molecules of air. And all of these things are bouncing around. And when they hit the edge of the pool table, or when they hit the kid's finger, they'd inevitably come crying up the stairs because somebody got their finger trapped in between a couple balls. There was an energy that was transferred right there, a kinetic energy of those moving balls. Well, the gas molecules are no different. This guy called Boltzmann came along, and he cooked this up for us. He wanted to know how to go from here to something related to temperature. And there's some of the gory details of that in your book, but the average kinetic energy is 3/2 kT. You will also see this sometimes called the RMS, which stands for root mean squared. This is a way to a statistical model, a statistical tool to get the average of something. If I think about a molecule that's moving this way with a speed of -4 and another molecule that's moving this way with a speed of +4, the average of that is 0. So I don't want these things to all cancel out, which they would. The average speed is not 0. So we kind of play this little game here where I'd take the two numbers, 4 and -4, and I would square them, and then I would average them, and then I would take the square, I forgot to square this one, take the square root of that to get back to my average speed right here. 4 squared would be 16, and -4 squared would be 16, and I'm dividing by 2, and so that's 32 over 2, which is 16, but I got to take the square root because, if I square it and then take the square root, I'm kind of back where I started. I get a root mean squared value of 4 there. I'm not interested in the direction. I want to know the speed of the thing, right? I want to know how fast on average these things are moving. So root mean squared does that very nicely. Now there's some other factors that can come into this thing. Here we're really talking about a single molecule, or maybe here would be just a single atom making up, like neon, for example, won't bond with anything, right? So that would be a single atom. If I have oxygen, it typically makes a covalent bond here like that. So I've got this oxygen and this oxygen, that makes O2. I can also have O3. I can also have CO and CO2, different molecules here, but that thing could move. It can also rotate though, and it actually can also vibrate. So there's different ways that these things can move, and I don't want to get too deep into that. This is good enough. All right. There's all this discussion in your book if you want to read about degrees of freedom and the temperatures at which things begin to vibrate and all that. For us, let's just go right here. All right. This is the root mean squared kinetic energy of an average molecule in the room right now. And we're going to use that. But check this out right here. If I want to find out how fast something's moving, find the average velocity of an oxygen molecule in my room. They give me the mass of the oxygen there. Look how easy this is. I come in and say, well, I've always known that kinetic energy was 1/2 mv squared, and now Boltzmann is telling me that I can get to that same number using 3/2 kT. So if I come in here and just set those two equal to each other, the kinetic energy is this, the kinetic energy is also that, those have to be equal, then we can make some hay out of that. You see real quick that the 2 on the bottom here and the 2 on the bottom are going to cancel like that. That would leave me 3 kT equals mv squared, and we were looking for the velocity, so I need to divide both sides by m. That would leave me v squared. I don't want squared, so let's take the square root of both sides, and it would look like that. The square root of 3 kT over m will give me the average, the root mean squared, whatever you want to call it. Sometimes you'll see a little bar on top like that, which means average, but not hard to do here. I'm going to come in and we'll say 3 times k. That k is Boltzmann's constant again, so I go back, right there it is, 1.38 10 to the negative 23 joule per Kelvin. I already forgot, 1.38 10 to the negative 23. 1.38 times 10 to the negative 23 joule per Kelvin. Right there, you see the Kelvin on the bottom, so you better bet that that temperature needs to be in Kelvin to make the units work out. If I'm in a room, then the temperature is something like 20 degrees Celsius. If I put 20 degrees Celsius right there, see how the Celsius and the Kelvin don't get along? So that is not correct. I need to come in here and add 273 and get 293 Kelvin. Put that in. And then divide by the mass, which they gave to be this little bitty number here. We're talking about 2 atoms of oxygen tied together. You know what, actually looks like that number's in grams. I don't want grams, I want kilograms. So we need to go another 3 spaces here. Negative 26. Can't get in there. There it is. Alright, kilograms, like that. And that is our number there. Now, I wonder what kind of number that would give us. Is this going to be a big number or a small number? When you think about a gas molecule moving around, how fast does that thing move? Well, this will tell us real quick here, but you might be surprised by this number. $478. Okay, and if you start picking apart the units here, just to see what that's in, this Kelvin cancels that one. I got a joule on top and a kilogram, and don't forget to take the square root of the whole thing. So here's joule per kilogram under a radical. A joule is a Newton meter. A Newton, let's pick that apart, kilogram meter per second squared, meter over kilogram. The kilogram cancels right there. I got a meter times a meter, which would be a meter squared. I got a second squared. It's all under a square root. That's a meter per second. We're talking about meters per second right here. 478 meters per second is the speed of that bullet, or the speed of that molecule there. And I said bullet because it's pretty close to, I'm multiplying by 3.28, and I'm getting about 1,600 feet per second, which, that's a bullet speed. So that's pretty remarkable. that the average molecule of oxygen moving around in every room, bouncing off your forehead, is moving at rifle velocities. Why doesn't it kill you? It doesn't have enough mass, right? It does have enough mass to create a little bit of pressure right there on your skin or on the inside of a balloon or something, but it's not enough to kill you. That's probably a good thing, huh? Got one slide here. This is all in the book. I don't want to do too much here with this, and I won't ask you on the test or anything, but I want you to know that this exists. You can do the calculation that says, wonder if this blue molecule here, and it's only blue just because we want to be able to see it and differentiate it from any other one, but as it travels, it's going to make a collision right there, and then it bounces and bounces, and then it's a long time and then a short time. We can calculate the average free path, the average length of this before it collides into another molecule or atom. It would depend on the pressure in there, right? The more gas that I have in there, for example, here I've got a volume and a number of moles that we're talking about here. R would be the size of that thing. If it's a great big balloon bouncing around in there, then it's going to take up more space, so it's going to have a shorter path length, lambda, or a path time, tau. And so all of those things factor into this thing. The time, of course, is related to the velocity that it's moving at. So there's a lot of different ways that you can kind of do these and shape these. The VRMS, for example, we've got an expression for that, right? And we could tie it back to temperature, which would cancel, so there's, you see these things written a whole bunch of different ways. Different people use different units, and they're trying for different results, but these are the two that your book end up with. You can go there and see the derivation of these if you want. It's just kind of an interesting problem to think about. How far is that thing going to travel before it, on average, hits another molecule, and how much time will it take until it hits another molecule? So that's kind of fun to think about. All right, and I think that's everything for today. Hope you have a great day. Save up your questions and bring them to recitation or office hours, or email me or something, and we'll figure it all out. Thank you very much.